Welcome back. In the previous lecture, we learned about qubit operators, which are represented by 2x2 matrices that refer to the chosen reference kets and bras. In this lecture, we discuss how we calculate the probabilities of the various outcomes of the measurements. So going back to where we started, the source emitting polarized photons, we now have seen that this photon emitted by the source comes in to the polarizing beam splitter. We can refer, as we did originally, to the vertical and horizontal polarization, and then we had these coefficients alpha and beta. And already then we noted that alpha squared, the square of this complex number, is the probability for getting the outcome labeled with +1, and beta squared is the probability for the outcome labeled -1. So these coefficients alpha and beta, we refer to them as probability amplitudes. And when we square the amplitudes, then we get the probabilities. So these are the squared amplitudes, and they give us probabilities. Now, what is true for vertical horizontal must also be correspondingly true if we refer to diagonal and anti-diagonal polarization, where we had the probability amplitudes of alpha plus beta divided by square root 2 and alpha minus beta divided by square root 2. So squaring these probabilities, alpha plus or minus beta divided by square root 2 squared, that will now give us the probability for +1 or -1, but not for this device, okay? Because now we are probing diagonal and anti-diagonal polarizations. So the polarizing beam splitter gives us the +1 outcome for vertical polarization and the -1 outcome for horizontal polarization. So it's the right piece of equipment if we want to probe for vertical and horizontal, as we did originally. But now we want to probe for diagonal and anti-diagonal. So we need to convert incoming diagonal polarized photons into vertically polarized photons that then are probed by the polarizing beam splitter, and incoming anti-diagonal photons into horizontally polarized photons that give us the -1 outcome. So this is achieved by having a half-wave plate at 22.5 degrees. So this half-wave plate converts diagonal polarization into vertical polarization and anti-diagonal polarization into horizontal polarization. So it's described by this sum of two ket bras. We can easily verify if we apply this sum of ket bras to an incoming diagonal photon. So it's a diagonal ket on the right. That diagonal ket with the anti-diagonal bra gives a 0, so this term disappears. And when the diagonal ket meets the diagonal bra, then that gives 1, and we are left with the bra that describes the vertically polarized photons. So this does indeed convert anti-diagonal to horizontal and diagonal to vertical. So this measurement together probes for diagonal and anti-diagonal polarization. Okay, so we now have two ways of probing the polarization of the incoming photon. Without the half-wave plate, we look for vertical and horizontal polarization. We get +1 and -1 as the outcomes, and these +1 and -1, they refer to the eigenvalues of what we call Z, which is the ket bra for vertical polarization, and from that we subtract the ket bra for horizontal polarization. And with the half-wave plate in place, we probe for diagonal and anti-diagonal polarization. And here we have the quantity X, which is the analog of this with diagonal ket bra, and the anti-diagonal goes with the minus sign. But in addition to vertical horizontal, diagonal anti-diagonal, we also had the option of referring to right-handed and left-handed polarization as the basic choices, and then we have the probability amplitudes of alpha minus I beta divided by square root 2 and alpha plus I beta divided by square root 2. And now the squares of these probability amplitudes, square root 2, gives us the probabilities for outcome +1 and -1 if the experiment probes for the quantity y, which is the right-handed with the plus sign, and left-handed with the plus sign. So rather than the half-wave plate, we now need a quarter-wave plate for converting right-handed polarization into vertical polarization and left-handed polarization into horizontal polarization. And so there's a third way of conducting the experiment, where we have a quarter-wave plate before the photon enters the polarizing beam splitter, and now the +1 and -1 outcome are associated with right-handed and left-handed polarized photons entering the device, which now consists of a quarter-wave plate followed by a polarizing beam splitter. So what all of these cases have in common is that we have probability amplitudes that we square to get probabilities, fine, but how do we get the probability amplitudes? Well, how do we get the probability amplitude alpha? Well, we have already seen that, and the answer is we calculate the bracket made of the bra for the vertical polarization and the ket for the incoming polarization. And then we square that bracket, and that gives us the probability. And likewise, if we want to have the probability for horizontal polarization, so then we have the horizontal polarization bra, the ket for the incoming polarization, and we square that bracket, that amplitude. And likewise, if we want to have the probability for finding diagonal polarization, well, it begins with calculating the probability amplitude for that, which is the diagonal bra, and multiplied with the ket for the incoming polarization. Then we square these numbers, and we get the probability for getting +1 if we do the measurement which has the half-wave plate in place, and so forth. So we get probabilities from brackets, and then we square them, the probability amplitudes from brackets, and we square them to get the probabilities. So if we look at this in a much more general way, then we would say that beginning with the incoming polarization, there is a polarization for which we probe, and for that I will just write a question mark now. And then that will be the probability amplitude that is associated with this probing. And when we square it, we get the probability for finding the question mark polarization if the incoming photon has its polarization described by the ket in. This is an example of what we call the Born rule, or Born's rule, which is named after Max Born, who was one of the pioneers who developed quantum mechanics in the 1920s and 1930s. So we have looked at polarization qubits as an example of a binary alternative as we have it in quantum measurements. But of course, there is nothing particular about polarization qubits. If we have other kinds of qubits, we will have the same mathematical machinery. So let's just talk about this in this kind of from this general point of view. So if we have some sort of qubit, so this could be polarization of a photon, but it could also be something else. Then we will have binary alternatives when we will describe, say, two of such outcomes that are clearly distinct, such as vertical and horizontal polarization, or right-handed circular polarization, left-handed circular polarization. We will describe them by such a pair of kets and the corresponding bras, and then an arbitrary qubit state would be written with amplitudes that go with this choice of alpha A1 and A2. So there will be probability amplitude, say alpha 1 and alpha 2. But of course, we can also have another choice for those basic alternatives, say B1 and B2, and then there will be probability amplitudes beta 1 and beta 2 that go with that. And as we just recalled, we would calculate the alpha 1 probability amplitude by taking the bra for A1 and the ket for the generic qubit state, and so forth. So over here, for example, we have beta 2 given by the bra for B2 and the generic ket. Now, what is important about these choices A1 and A2 is such that if I have A1 and A2, the bracket that will be 0, which is just saying that if my qubit is prepared such that it has the property described by A2, it will not have the property described by A1. And then we have the normalization, which says that if the qubit is prepared with the property described by the ket A1, and then we probe for that probability, we will find it with certainty. So the probability amplitude is 1, and then the probability that you get from squaring that will also be 1. And so that will also be true for the A2 bracket, and similar for the B1, B2 bracket, and those that go with B1, B1 and B2, B2. So we have seen this in all kinds of examples by now for vertical, horizontal, diagonal, anti-diagonal, and so forth, all these properties here, but they simply generalize to what we need for the description of qubits of other kinds. So the physical meaning of A1 and A2 and B1 and B2 will much depend on which kind of qubit we talk about, but the mathematical machinery is very much the same. And then, of course, we get the probabilities, as we just saw, by squaring these probability amplitudes, and say the probability for finding the property described by B2, well, we will square this probability amplitude. And then, just like we had these quantities that we called Z and X, we have corresponding quantities here, which would be the, say, for the Z, maybe I should call this just A. We have a quantity, say A, that is A1, A1 minus A2, A2. So that's the analog of what we call Z for vertical and horizontal, and there could be a quantity B that is likewise constructed for B1 and B2, and so forth. So whatever we did for the polarization qubit simply carries over to qubits of other kinds. So there is a rich enough mathematical formalism that we got acquainted with by looking at the particular physical example of a polarization qubit. but we have exactly the same machinery for qubits of other kinds. In summary, the Born rule tells us how to calculate probabilities. That is, we square the probability amplitude, the bracket for the system ket and the outcome bra. Further, we recognize that the mathematical formalism developed for the polarization qubits is also suitable for qubits of other kinds. In the next lecture, we will go beyond the binary alternatives of qubits and will consider measurements that have more than two different outcomes.